So now let us start with power system security, a part of module 4. So when it comes to power system security, it can be defined as the practices designed to keep the system under operating limits with when components fail, or we can say that ability of the system to regain its normal operating condition after being subjected to a contingency. Contingency is nothing but failure of an equipment. So already we have seen the definition of security when we were dealing with security. Now here in detail we'll go with analysis involved in security. So first we have to define the levels of security. Level 1, secure level. At this particular level, all the loads will be supplied without violating the limits, and none of the contingencies will cause violation of system variables. That means all loads are being supplied. That means there is adequate generation or sufficient generation to meet the load requirements without violating the limits. Violating the limits means we are not violating the power flow limits as well as bus voltage limits. Voltage at the buses are not violated. At the same time, power flow limits are also not violated, and none of the contingencies will cause violation in system variables. System variables refers to frequency and voltage. These system variables also will not be affected. Level 2 is correctively secure state. So in this case also load is being supplied without limit violations. In case there is an equipment failure or contingency, by taking necessary control actions, system can be corrected without loss of load. That is, without compromising with loss of any load, we can bring back the system into normal state. That's why it's called correctively secure. Level number 3 is called as alert mode. In this case, load is supplied without violating the limits, but a contingency may cause violations which may be corrected without loss of load. So the contingency will cause the deviation in the system variables like frequency and voltage. So this is called as alert mode. Fourth one, correctable emergency. Here again all loads are supplied, that means adequate generation is there. Operating limits are violated, that is bus voltage limit violation will be there, as well as power flow limit violation will be there. These levels can be corrected by suitable control action without loss of load. So here we can understand that without loss of load, the corrective actions can be taken. So this is called as correctable emergency. Since operating limits are violated, it is called as emergency. Level number 5, non-correctable emergency, where all loads are supplied but operating limits are violated. This cannot be corrected without loss of load. That is, we have to compromise with some loss of load, then only it can be corrected. Otherwise, it cannot be corrected. So it says non-correctable emergency. Then level number 5 is over. Level 6 is restorative mode. In restorative mode, there are no operating limits violated, but system is operating with loss of load. All the system variables are normal, but there is loss of load. That means you can understand that if you take a particular locality, 2 or 3 streets are not having power at all, and remaining part of the area is having power, and there are all the system variables, frequency, voltage, everything is operating nominally. The variables are nominal, but few streets are not having power. That is what is called as loss of load. With loss of load, everything is secure. This is called as restorative mode. So at any point of time before planning for the next action, we should know in which level the system is, then only we can take appropriate action. That's why we try to understand the security levels here. Then we talk about factors affecting the system security. One is line outage, the other one is generator outage. That is failure of a transmission line, failure of generator. These are the major factors. Next, we'll talk about functions of power system security, system monitoring, contingency analysis, security constraint optimization. So when it comes to system monitoring, we'll be using SCADA to monitor all the system data like frequency, voltage, active power flow, reactive power flow, losses happening in the line. All these information will be monitored using SCADA. Next section is contingency analysis, wherein we'll go for simulation. Before checking the system in actual condition, we try to simulate the failure and take the necessary corrective actions. So under this we have contingency definition, contingency selection, contingency evaluation. So what we exactly do in contingency definition is list all possible contingencies. List all possible contingencies means try to list all the possible causes of failure, all the possible equipments that can fail. Transmission line can fail. Any number, say 10 transmission lines are there, means we can consider failure of each and every transmission line. Then failure of transformer, maybe failure of generator, any equipment may fail. So we'll list all the possible failure possibilities. Then contingency selection. Shortlist the contingencies or ranking in the order of severity. So whatever list we have prepared, possible failures, among that which is more severe, which is less severe. So in that order, we are going to organize it. That is called as contingency selection. Then contingency evaluation. Try to simulate the effect of that contingency on the system. That is, try to simulate for failure of a particular transmission line in the software and check what impact it will have on the rest of the system. So this is nothing but contingency evaluation. Once the contingency evaluation is successful, then before the actual failure happens, we can take the corrective action. Accordingly, we can plan for that. That happens in security constraint optimization. So now here we can see the effect of this operation. Let us consider 4 stages. Stage 1, we have unit 1, generating unit 1, we have generating unit 2. The generating unit 1 has a capacity of 500 megawatts, generating unit 2 700 megawatt, and we have the transmission line capacity as 400 megawatt. That is, each of the transmission lines can supply power at 400 megawatt. We have 2 transmission lines here, and load is in the vicinity of unit 2, and the demand is 1200 megawatt right now. In this particular case, we call it as optimal dispatch, where 700 is supplied by unit 2, 500 is supplied by unit 1 via 2 lines. In first line we have 250, another line we have 250. Totally unit 1 is supplying 500, unit 2 is handling 700. So the characteristics are: system may not be secure, there is no contingency in this particular state, and load dispatch is economical. Yes, fine. Coming to post contingency. Post contingency means after the occurrence of contingency or failure. What failure we are simulating here is failure of a transmission line. Suppose if the transmission line 1 breaks due to some reason. Breaks in the sense the power supply may be cut off, or there may be a physical breakage of the line, maybe a physical damage, or it may be due to some overcurrent, it would have tripped. At that point of time, all the 500 megawatt now will be on line 2 itself, but transmission line has got its capacity to be 400 megawatts only. When you try to send 500 megawatts, it will be overloaded. So there is a problem here. So system will not be secure anymore. So this is what is going to happen. Now, since we are running the simulation program, we can plan for this well in advance. And what we can do is, we have now got to know that if line 1 fails, this is the condition that can happen. That is post contingency condition. So in order to avoid that, we go for secure dispatch, where we try to transmit 200 and 200 from line 1 and line 2, such that unit 1 is supplying totally 400, and unit 2 will be enhanced to 800 megawatt. So in the next stage 4, since we have taken corrective action, if there is a contingency, 400 can be safely transmitted through the line from unit 1. So there is no trouble. So this is the action that we can clearly take. Then we talk about contingency evaluation techniques. Contingency evaluation technique means, in order to do the simulation, what are the methods we are using, what are the algorithms that we are using, One is DC load flow, the other one is AC load flow. So in case of DC load flow, we'll be using FDLF algorithm that we have discussed in module number 2. And in FDLF technique, interaction between PV and Q delta are neglected, as you very well know. And then this algorithm does not give information about voltage limit violation and volt ampere reactive flows after a contingency. That is the disadvantage of DC load flow in FDLF method. In this method, contingency ranking is done based on A and D factors. Later on, we'll see what are A and D factors. In AC load flow, Newton-Raphson algorithm, which is more popular, which is time consuming but most accurate, is used. Also, we have seen many problems on Newton-Raphson in module number 2. This will give us the complete information with utmost accuracy. This depends on performance index. Ranking of this will be done based on performance index. Next, we talk about contingency analysis, DC load flow or AC load flow. Depending upon the requirement, we choose the right option. And the major factors that we are going to consider are line outage and generator outage. So the impact of them will be studied with a flowchart. So in this flowchart, you can see initially we initialize the system model. N is equal to 1. That means we start to check for the first unit. Simulate nth unit outage. We try to manually simulate the failure of some nth unit, the nth generating unit. Then check for the line flow limit violation. Because of this planned outage, is there any line flow limit violation, that is active reactive power that is flowing on the transmission line? Is there a violation in the limit? We are going to check. If there is a violation, generate or give alarm signal. If no, check for the next thing, that is any bus voltage crosses the limit. We have to check whether any bus voltage has exceeded beyond the limit. If yes, give an alarm signal, otherwise continue to the next. All units considered, that means we have checked only for nth unit outage for one generating unit. We have to check for all the remaining generating units one by one. Try to disconnect a generating unit, check whether it will have a negative impact. A negative impact in the sense line flow limit violation is there or bus voltage violation is there, just check for that. If nothing happens, continue. If there is a problem, generate an alarm signal. This finishes first part of the flowchart, and the next part of the flowchart we have simulate ith line outage. In the first part we have checked for generating unit outage. Here we check for line outage, transmission line failure. If is there any line flow limit violation? If yes, generate alarm signal. Otherwise, check for bus voltage limit violation. In case it is, give alarm signal. Otherwise, continue. Check whether all the transmission lines are considered. That is, go on disconnecting every transmission line and check whether it will have a negative impact on the system. So this completes the flowchart for contingency analysis. Then here we define the A and D factors that I was talking about. Network sensitivity factors. It is defined by change in megawatt flow on line L divided by change in generation at ith bus. So line flow post contingency is equal to line flow pre contingency plus change in line flow. That is the power that is flowing in the transmission line plus the power that is flowing before the occurrence of the failure should be equal to power that is flowing after the occurrence of failure. So this defines the A factor, that is change in power flow on line L divided by change in generation at ith bus. Then another factor is distribution factor, which is defined by ratio of change in active power flow on line L divided by pre-contingency line flow on ith line. That is, before the occurrence of contingency, what was the power flow on that particular line, defines pre-contingency line flow on ith line, and FL, delta FL represents change in megawatt flow on line L. So this ratio will give us DL. So these are A factors and D factors. They will be calculated in DC load flow. And the last one is performance index. In AC load flow, we depend on performance index for ranking the contingencies, that is listing the contingencies based on the severity. So PA is defined by ratio of power flow after contingency divided by megawatt capacity of a line. Power that is flowing after the effect of contingency, that is equipment failure, divided by the actual capacity of the actual power carrying capacity of the line. Then voltage deviation divided by value fixed by the utility. Deviation in the voltage due to this contingency divided by the expected value fixed by the utility. This ratio of performance index pertaining to power as well as voltage, if added together, will give us the actual performance index, which is PI. So contingency ranking will be done based on PI in AC load flow. Depending on A and D factors, severity will be decided in DC load flow. So this completes the concept of power system security. However, some other part of power system security will be continued in your 8th semester subject, which is power system operation and control. Further, some more concepts will be continued over there. As per the 7th semester syllabus, this is the concept of security.